All right, that way that I was going with it would work, but it would require using integration by parts. And there's an easier way of doing it. And so I'm going to start over with this. The work done, the kinetic energy is the integral of f dx. Okay, so here the f, I'm just going to plug in what f is here, because we already have that from our previous calculation. So that's m naught times a divided by 1 minus v squared over c squared to the 3/2 power times dx. And then I'm going to change variables by writing dv dt as dv dx times dx dt using the chain rule. And then the dx's will cancel, and then that's divided by 1 minus v squared over c squared. Or that gives us here just m naught v dv divided by 1 minus v squared over c squared. Okay, so basically what I've done then is I've converted this into, by change of variables using the chain rule, into an integral over the velocity. Okay, and so this is not that much different from how I derived the kinetic energy as 1/2 mv squared in Physics 208A, which you may or may not remember when I did that. But all I've done here is that same thing, using that same chain rule, but with an expression for the relativistic force, which gives me this extra term in the bottom. If I didn't have that extra term in the bottom, this would just be the integral of m dv dv, which would just integrate out to 1/2 mv squared. Okay? But it's a little trickier than that, because now we've got this denominator term, which is how the relativistic force changes as the velocity approaches the speed of light. Okay, so once we've reached this point, we can now use a u-du substitution. We can let u equal 1 minus v squared over c squared. So du then is just minus 2v over c squared dv. Okay, and so we've already got a v dv in the numerator. Okay, and so all we have to do to turn this into a du then is to multiply by minus c squared over 2v. Or no, not c squared over 2v, just c squared over 2. Okay, so we've got the m naught in there times c squared, right? And then to turn this into a du, in the denominator, you have to multiply by minus 2 over c squared. So I'm doing minus c squared over 2 on the outside. So that gives me then just m naught times du over u to the 3/2 power. Okay, and so then that becomes u to the minus 1/2 power divided by minus 1/2. So that's minus m naught c squared over 2 times u to the minus 1/2 power divided by minus 1/2. But the same thing as dividing through by minus 1/2 is the same thing as multiplying through by minus 2. And so then this is going to be integrated from 0 to v. Right? So then the minus signs are going to cancel, the 2's are going to cancel, and so our kinetic energy then is going to look like m naught c squared times 1 over 1 minus v squared over c squared to the 1/2 power, evaluated from 0 to v. Okay, so when it's evaluated at v, we just get this expression. When it's evaluated at 0, it just gives us 1. So this is going to be m naught c squared divided by square root 1 minus v squared over c squared minus m naught c squared. All right, so that's the right answer. This may not look quite like E equals mc squared yet, but let's just take that result, move it over to this side. We've got that result as k equals equals m naught c squared divided by square root of 1 minus v squared over c squared minus m naught c squared. What Einstein realized, if this is the kinetic energy, then we've got this term which is velocity dependent and this term which is not velocity dependent. And so he equated this then with the rest energy. What this means then is that this is the energy that a particle would have if v equals 0. So you could think of this as being its latent or, in a sense, potential energy, if you want. Not quite potential energy, but it's kind of like that. This is the kinetic energy, which is the difference between this term and that term. So he said, well, this must be the total energy. So the total energy then is going to be mc squared equals k plus m naught c squared, where m here is just our relativistic mass. M is equal to m naught divided by square root 1 minus v squared over c squared. And so this then is total energy equals kinetic energy plus rest energy. Or E equals mc squared, but with a relativistic mass. This is our rest energy, which is the inherent energy in a system that has 0 velocity. And this is our new expression for kinetic energy. Okay, so if this in fact is our expression for kinetic energy, then it would be comforting, before we go any farther with this, to verify that it reduces to 1/2 mv squared in the limit when the velocity is less than 1/10 the speed of light. So let's do that first. Let's show that k excuse me, equals 1/2 mv squared for v much, much less than c. How are we going to do that? Well, one way we can do this is to, let's look at the square root term. So the k then is equal to m naught c squared times 1 minus v squared over c squared to the minus 1/2 power. And then we have minus m naught c squared. Okay, so I'm going to write it that way. And then what we can do is a binomial expansion here, where one plus x to the nth power is equal to approximately 1 plus nx for small x. Okay, now our binomial expansion is actually going to have a lot of other terms in there. We're going to have 1 plus nx plus n times n minus 1 x squared over 2 factorial plus a whole bunch of other higher order terms. But when x is small, these higher order terms go to 0. So that we can write the binomial expansion for small values of x, in this case x is minus v squared over c squared, as just 1 plus nx. And that'll give us a very good approximation. We know that the velocity for anything that's less than 1/10 the speed of light is going to be on the order of just here 99.5% the speed of light. Isn't that what we said before? Okay, so to a very good approximation, then we don't need the higher order terms in our binomial expansion as long as x is small enough. And so that is the case here, where the velocity is less than 1/10 the speed of light. All right, so our x then is minus v squared over c squared. And so the kinetic energy then is going to be m naught c squared times 1 plus n. Now n here is going to be minus 1/2 times x, which is minus v squared over c squared. Okay. And then that's going to be minus m naught c squared. Right? So we've got this term then, and that's just 1 plus n, 1/2, times x, where x is minus v squared over c squared. And then that's going to cancel out this negative sign. And so what we end up with then is just m naught c squared. And here we've got, this is minus 1/2 and that's minus. So those two minus signs cancel. So we get plus m naught c squared times v squared over c squared. And then we have here minus m naught c squared. So the m naught c squareds cancel. And here the c squareds cancel in the second term. So what we end up with then is just k equals 1/2 m naught v squared. And so that's it. That's our non-relativistic kinetic energy. And we see that it does, in fact, reduce to what it's supposed to when we take the kinetic energy expression and take the limit for v being small in relationship to c. So that means that this x value, which is v squared over c squared, is small. If v is, say, 0.1 c, then this becomes 0.01. Okay, and so then that's 1 minus 0.01. So we're dealing with a small value for x, 0.01 versus 1 here. It's just 1%. And that's even at that very, very high speed. It's still 1/2 mv squared. Okay, so if you were told that a particle had a certain amount of energy in terms of the kinetic energy, let's say you were told that a proton has a velocity of, let's say, 10 to the 7 meters per second, and you want to know whether this is a relativistic problem or not. What you could do is you could say that associated with this, you could plug in for the, actually let's do this slightly differently. Let's say that the proton has an energy of, let's make it 10, let's make it 100 electron volts. Okay. So that's our kinetic energy. So what does that mean? Well, it means that Q times the voltage difference is equal to energy. Okay, and so here, the charge is the charge on an electron, 1.6 times 10 to the minus 19 coulombs, times 1 volt, then the energy that that has is going to be 1.6 times 10 to the minus 19 joules. So that we can also define as being an electron volt by definition, because if we take a charge of an electron accelerated through an electric potential of 1 volt, then that gives it a certain amount of energy from physics 208b. Okay? And so this is the definition then for a new kind of energy. Now why do we use electron volts instead of using joules? Well, because the kinds of numbers that we're dealing with are very small, okay, when we're dealing with subatomic particles, and like electrons or protons. And so if we start talking about this number of joules and it's such a small number, it's better maybe to use another scale where the numbers are more reasonable. Okay, just like if I'm trying to measure the distance across this room, I'm not going to use millimeters, I use feet. Okay, because that gives us a more reasonable number for the length of this room in terms of a different set of units. And so oftentimes then you'll be given an expression for the energy in terms of electron volts rather than in terms of joules. So let's do that then with this problem. Let's say that the proton has a kinetic energy of 100 electron volts. Is it relativistic? Okay, so the check then, and this would be a relatively easy check to do. You could say, okay, well, no problem. I'll just go back to this expression over here for relativistic kinetic energy, and I'll plug in for here 100 electron volts, and then I'll solve this equation for V. Well, no thanks. I think what I'd rather do is just do a quick check using the 1/2 mv squared. Okay, and see if V, so our check then is if K is equal to 1/2 mv squared, gives a velocity that's less than 0.1 c, then I know that this was a valid assumption to make. Then non-relativistic. However, if this expression for the kinetic energy gives a velocity v that's, for example, greater than c, then it must be relativistic. Because only as we get to closer and closer velocities to c does the increase in mass start becoming significant, and that changes the kinetic energy expression, and we must use the relativistic K. All right, so that's what I'm going to do here. So I'm just going to check this and see whether 100 electron volts gives me a velocity that's less than 1/10 the speed of light. So if I solve this for V using this expression for the kinetic energy, I get V is equal to the square root of 2K over m. Okay, so that's going to be the square root of 2 times, and then here's the K. Okay, so when we say an object has an energy, a lot of times in the textbook you'll see that what almost always are referring to is the kinetic energy, and not usually the total energy. So when they say a particle is accelerated to this energy, they're talking about it being the kinetic energy part of the total energy term. All right, so this then is going to be 100 eV times, and now we're going to have to convert this into joules, 1.6 times 10 to the minus 19 joules per eV. Then we'll divide that by the mass of a proton, which is 1.67 times 10 to the minus 27 kilograms. And I'll give you this if you need it. All right, so let's knock that out and see if we've got a velocity that's less than 1/10 the speed of light. All right, so what that's giving me here is 1.39 times 10 to the 5. Meters per second. All right? And so you go, well, that's fine because 0.1 c is 3 times 10 to the 7 meters per second. So this is way less than 1/10 the speed of light, and so therefore a proton that has this kinetic energy is non-relativistic. Okay, so that's a quick and easy way to determine whether the object has a relativistic energy or not. Okay? Another thing that I'd like to take a look at now is what happens, or at what velocity, I should say, and now we're going to get relativistic, because we know that if we get up to like 70, 80% the speed of light, then it really starts, the relativistic effects start getting big. And so let's ask here in this question, at what speed will the rest energy equal the kinetic energy? Okay, so basically then we're back to this expression. You can say that the total energy is m naught c squared divided by 1 minus v squared over c squared. That's equal to k plus m naught c squared. So this is our kinetic energy. This is our rest energy. This is our total energy. Okay? And so we're asking then, at what velocity will the rest energy equal the kinetic energy? Okay? Another way of saying this then, restated, is if the kinetic energy equals the rest energy, that means the total energy is twice the rest energy. Because k must be equal to m naught c squared, so we can just rewrite this as 2 m naught c squared. Now why not 2k? Well, because I have a common factor of m naught c squared on the other side of the equation. So it's going to make more sense to write the kinetic energy in terms of m naught c squared if I want to solve for my only unknown, which is the velocity. All right, so let's do that here. M naught c squared divided by square root 1 minus v squared over c squared equals 2 m naught c squared. Okay. And so then I can cancel out the m naught c squareds. And what I'm going to get then is 1 over root 1 minus v squared over c squared is just equal to 2. I can cross multiply. It gives me 1/2 equals square root 1 minus v squared over c squared. Square both sides of the equation gives me 1/4 equals 1 minus v squared over c squared. And then solve that for v. And so if I do that, then I get v squared over c squared equals 1 minus 1/4, or v squared equals 3/4 c squared, giving me finally v is equal to the square root of 3/4 c squared, which is just root 3 over 2 c. And so this is 0.866 c. So the velocity then is 86.6% the speed of light. The rest energy equals the kinetic energy. Okay, so that's a simple enough thing. If I had over here asked you at what velocity is the kinetic energy equal to twice the rest energy, then you'd put in 2 m naught c squared here. Here you put in m naught c squared. That would give you a 3. And that 3 would become a 1/3. That would become a 1/9. You could work the whole thing through. And so I could do that with any multiple, let's say, of the kinetic energy being that much more, for example, than the rest energy. And that, I think, would be a fair problem for a quiz or an exam.